Adiabatic quantum machine learning, and off we go.
Right, thank you. And thanks a lot to the organizers for inviting me to speak here. So I'm going to talk about adiabatic quantum machine learning. I now work at the Information Science Institute of USC. We have a small group there. Federico Spadalieri, who is also here, is involved in all this work. Also, Greg Verstek is working with us. He also works on classical things, but he's contributing a lot to the kind of stuff, the quantum effort, let's say. Kristen Pudens, who's a PhD student of Daniel. Daniel Lidar, who's actually at USC, but we're very involved with him. And luckily, there is a lot of very good people at USC, and actually, well, Stefan Haas, Paulo Solari, Todd Brun. There is also Bernd Reichert just moved there. I forgot to update this. So that's also pretty good. The reason why I work at ISI is because there is a D-Wave machine installed there. So we're trying to do several things with it. One is, and that's basically what a lot of these people are interested on, trying to understand the physics and the potentiality of this device and what is capable of doing it. But there is also something else we need to do, which is assuming that this machine is actually performing up to specifications and maybe even better. What kind of problems can we actually run on it that are of practical interest? In particular, there are 108 working qubits here, and a limited number of couplers between the qubits, 255 to be exact. So it's kind of a sort of a 2D Ising model, extended Ising model with random couplings and bits, limited precisions in the couplings and the local fields. So what kind of problems are interesting to run in this machine? Problems, let's say, of practical interest, not just physics problems, which is also very interesting for us and people at USC. So we're lucky that we're not the first ones thinking about this. Of course, D-Wave has already been thinking about this for some time. And in particular, there is this string of work by Harmon Nevin, who's here, and Basil, who's also here, and people at D-Wave like Bill McGreevy and Jordi Rose, trying to address this question. This effort has been going on for some time. So we are building up on what they have done already. And what I'm really going to be talking about is an application of the kind of technology they have developed. There is also a recent paper by Kristen, who I think actually has a poster about this stuff, Kristen and Daniel. And the technology is called adiabatic quantum machine learning. Okay? So I'm going to take a little bit to actually get to the quantum part, but because that's the problem we're trying to solve, and I think it's a very interesting problem on its own. But eventually you will see where the quantum bit comes on. And if I have time, I will maybe talk a little bit about some of the physics and more elementary kind of experiments that we're trying to do with the chip to understand it better, how it functions. But for most of the time, it's just, if it functions as it's supposed to, what can we do with it? So last year, I was a postdoc at Alan Spurugussi group. Alan talked here on yesterday, I guess. And so he has a very big group. As he explained here, one of the things they do is they do trying to apply quantum computation to solve chemistry problems. And that's what I'm going to talk about today, applying adiabatic quantum machine learning to quantum chemistry problems. And some of the people that has been involved on this particular application, maybe not on the application, but on the project itself, that we're trying to solve is Johannes and Roberto Olivares. And Roberto Olivares is also working on this adiabatic quantum machine learning part, but it's actually a big project, so Sule works on that. And, well, probably more people in the picture. Are you the one in the mask? Yes, no. I could be, that's what Alan says when I am around. But no, it's not me. Okay, so yeah, as I was saying, it's quite a big project. It also involves people from Stanford, experimentalists, Professor Sinan Bao, Well, there are parts of it that involve calculations doing a DFT, so QChem, and it's also a project that runs on it's a screensaver, and it's part of the IBM World Computing Grid, so you can just Google for the Clean Energy Project and download the screensaver, and you can be running DFT computations when you're not actually using the computer. That will help this particular project. And what the project is about is trying to optimize organic photovoltaics. Organic photovoltaics are solar cells, and they can be quite cheap to produce because they are basically plastic. And see if you can make a good organic solar cells, which is cheap to produce, that will be very useful for everybody. So this is a little movie that Lauren, who's a student in the Lance group, produced. If the movie works. No. Then you need to click on the movie. It's not very important if it doesn't work. Okay. So it's kind of a fancy movie. What you have is this plastic is made of two types of molecules. These molecules here are the donors, the blue molecules here. That's what we're trying to optimize. A photon hits the donor, it creates an excitation. The excitation travels around the donor. It gets to the acceptor, which is this Fullerene molecule. And this is not real time. At some point, the excitation will break down. It will be an electron that travels to the Fullerene around now, and a hole that stays on the donor. So then the hole travels around the chain of donor molecules, and eventually it gets here, which is titanium oxide. This is the anode, and the electron gets to the cathode, so you get a different in voltage. So it basically works like this, right? And the point is that we really understand fairly well what's going on here at several levels of complexity, but it is really a very complicated problem that involves a lot of quantum chemistry and a lot of properties that are really hard to simulate. So even though we know what we want and we know how to describe it mathematically, it is really, most problems in quantum chemistry at sufficient level of sophistication, you cannot just solve it exactly. So, and the problem was actually, I don't know if I mentioned it explicitly, is to optimize the donors. So the donor were the blue molecules, in this case pentacene, and you want to, the acceptor, turns out Fullerene is quite a good acceptor, but it's been found experimentally by groups that are working on this, that changing different donors actually can increase the efficiency and durability and several properties of these organic photocells. So that's really the problem, coming up with better donors for organic photovoltaics. Okay, so that's the aim of the Clean Energy Project, which has several parts. One part is the molecule generation. So the input of the group at Stanford, Ball's group, was very important there to sort of say, well, these are the kind of molecules that we can actually build in the lab. That generates, well, Alan, and that was basically Roberto, I think, generated a library of like 10 million molecules that are reasonable, so for experimentalists to build. And the idea is what of those 10 million molecules is best for organic photocells. So you need to calculate things in those molecules. You cannot really calculate the whole process that was on in the movie, but you can calculate several things which are interesting. And in particular, that's the screensaver. So that's the main thrust of this project that has been going for 3 years, way longer than when I joined the project and the Lance group. And that's the screensaver, and it's basically doing DFT with different basis sets of functions and different functionals, things like that. So that's what the screensaver does. So once you have the data for the molecules that experimentalists can prepare, what you would like to do is to apply what is called cheminformatics to answer the problem that you're posing, which is which of these molecules are better. So that's the part where we're going to be using the adiabatic quantum machine learning and machine learning in particular. Okay. So the property that you really want to predict out of these molecules is the power conversion efficiency, which is basically the ratio of the power coming out the power coming in, so that's solar power, and that's the power you can actually get out of the solar cells. And it basically varies from, okay, initially, first devices were around 3.3% efficient. More recent devices get, changing the donor molecules, basically, and other things in the design, but they get efficiencies of up to 7.7, which is actually quite good, not as good as silicon, but these things can be cheaper and flexible, and they have other nice properties. So that's the whole thing we want to achieve. Donor molecules that increase this efficiency. So, because we cannot really build a chemistry model which is complete to solve this problem, that's why we need the machine learning part. So the machine learning does the following. There are 200 molecules. Actually, now Alan told me they have 400 molecules characterized that different experimental groups have already tried and build devices with, and they report the efficiencies. And we can use that as a training set, okay, to try to learn how to classify, how to predict the efficiency of arbitrary molecules. So that's going to be our training set. That's experimental data. Then there is the library of molecules, the 3 million ones. This is actually a couple of months old. That's the data that Alan's group has already calculated with the screensaver. So at the end of the project, it will be 10 million molecules. And you want to learn from the training set how to predict the efficiency. Okay, so these are just representative molecules that you want to understand. Whoops. Okay. They have actually published a paper where they do linear fitting, and that was the previous slide that is not coming up. So it's a very interesting paper where they, they find that indeed in the 10 million molecules, not surprisingly, at least with a linear fitting and a reasonable set of descriptors for each molecule. So the descriptors are the numbers you calculate with DFT or some other software that you can then use to do a linear fit. And they think that you can get efficiencies which are much better than the ones already reported in the literature. But a linear model is not optimal. So the idea is to improve that. And eventually what we would like to have is something called a Gaussian process, which is quite more sophisticated fitting than just a linear model. And it's not really the important point here in my talk, but it's basically the idea is you sort of work with a Gaussian distribution over an infinite space, which is a space of functions. And the space of functions are the ones that describe the model. And what you're going to do is from your training set, you're going to sort of estimate, doing Bayesian statistics, basically estimate what in that space of functions, what subsets are good functions for your fitting. So you actually get not only a function that sort of tells you what efficiency different molecules will have depending on your descriptors. You also get things like uncertainty, like if a molecule is here, you don't have much data about that, so then you're not really good about your numbers. So this is a very nice and sophisticated fitting model, which we're planning to use. The problem you have with this, for this case and others, is because we actually have quite a small training set, which is what our experimentalists have been able to implement and measure, and that's 400. But we can generate a lot of numbers describing each molecule, doing DFT calculations, and other type of structural calculations, of kind of quantum chemistry calculations. We actually have a much bigger set of variables or descriptors describing each molecules than the ones we can actually use successfully with a Gaussian process. So we need to constrain the number of descriptors that we're using for each molecule. So that's what we're focusing on. Well, this is kind of a problem. Okay, so there's a problem with the slide. But basically what we're doing is we use this commercial software, which is called Dragon. It's a cheminformatics software just to bootstrap this technology. Later we will use the DFT data coming from the screensaver. And so Dragon gives you like 6,000 descriptors actually, but we're only keeping so far like 600 of them. And for every one of these descriptors, we build what is called a weak classifier. So what we're actually trying to do first is, instead of just directly fitting with a Gaussian process, we turn the problem into a simpler problem, which is just a binary classification problem where we try to predict if a given molecule is good for organic photovoltaics or not. And there is some complicated process to that, which involve clustering and standard machine learning techniques. But once we have this binary classification process, then for every one of those descriptors, we build what is called a weak classifier that just says, well, given the number that I get from this particular descriptor describing the molecule, I think the molecule is going to be good, or the molecule is going to be bad. And because one number is not good enough, then every one of those weak classifiers is actually not a very good predictor. So you get a lot of noise if you just use a weak descriptor for your classification. But what boosting does for you is you build a strong classifier there are different versions of this, but versions reported on this adiabatic quantum machine learning approach. You can just do majority voting of a small set of descriptors. And even though every descriptor is kind of noisy when you do majority voting, if you select a good set of descriptors, the noise averages out, and it turns out that the descriptor can be good. And in theory, although it's not known for this particular approach, but for different boosting algorithms, it's been proven that you can learn whatever training set if you run enough times with your training data using boosting. So that's kind of part of the interest in boosting. So that's what we're after. We're after a strong binary classifier. And the idea is that once we have the set of descriptors, because every descriptor corresponds to, well, once we have the set of descriptors for the binary classification, those are the descriptors we can use for the Gaussian process. Okay, so what we do next is we check that the whole approach makes sense. And so one way to check that the whole approach makes sense is, well, we want to check that there is no like one particular or two particular descriptors that already solves the problem. And then you don't really need, out of the 600 descriptors, you don't need to keep like 30 or 40 for your Gaussian fit. Maybe just one or two contain all the information. It's very unlikely because this process of that goes on organic photovoltaics is quite complicated. But, it's good to check for that. And it's also good to check that the numbers actually give you information that you can use to solve your problem. So the first thing we do is just build a strong classifier which has only between 2 and 4 descriptors. Actually, this is one with only 1 descriptor. So between 1 and 4 descriptors. And because we're looking for strong classifiers with very few descriptors, we can actually just look at all the strong classifiers with 4 descriptors and see what kind of errors we get, just to see if there is a classifier that is extremely good on using only 4 descriptors. So we can do that doing an exhaustive search, and we have like a 10% errors. And the kind of descriptors, that was some of the slides that for some reason the presentation jumped over, are like the Berdin matrix, which is just a diagonal matrix, which has the atomic weight on the diagonal and of diagonal numbers related to the kind of bonds you have between carbon-carbon atoms. So if you have double bond, triple bond, single bonds. So it's kind of similar to the Haeckel model, or you have descriptors that are structural descriptors like Moore and autocorrelations, and these ones seem to be picking things like if you have sulfur atoms space in your chain, because that kind of has been known to increase exciton mobility, which is one of the things you want. So we're getting interesting descriptors this way, but the error is still quite big, around 0.05. So we would really like to increase this, and for that, we will need to get more descriptors involved, and we cannot do that with exhaustive search because it just takes too long. So now we have an optimization problem, which is build a strong classifier out of majority voting with more than 4 descriptors. Okay, so we solved that optimization problem, and this is data solving that optimization problem using a genetic algorithm. So this is kind of basically our first runs of this to see that we can actually increase the error, which we do from 0.5 to things like 0.05. And the optimization problem is just get me, so this H here is a Heaviside function. This is the QW is the strong classifier, depends on W, which is a binary vector that tells you which descriptors you are picking for that particular strong classifier. So this thing, sum over all F, is basically a measure of how many molecules you're classifying correctly in this binary classification problem. So this whole thing is just telling you how good this particular strong classifier is. So that's the function you want to optimize because you want strong classifiers that are pretty good at classifying these molecules, right? Now, if you just do that, you can have a problem, which is very common in machine learning, which is overfitting, where you have so many descriptors and you don't have that many molecules because there is no data for a lot of experimental data for a lot of molecules. So you can probably, just by choosing enough descriptors, fit your data perfectly, but then that won't generalize well because you're learning your training set. You're not learning, how to do a good model for predicting organic photovoltaics. So then how you solve that problem is you add this regularization term that counts the number of descriptors that you're adding, and every time you add a descriptor, you pay a penalty. So that's a standard machine learning. So we do that, and we see that as soon as we turn on regularization, we get an error which is around 0.005, so that's very good. And we get a set of descriptors which is around 30, which is actually very good because for 200 molecules, which is what we were using for this, you run roughly around 30 descriptors. And those will be the 30 descriptors that then we can fit into the Gaussian process. So the conclusion from this is that this model is indeed working well, and it's what is called a learnable model, and the descriptors that we get from the Dragon software indeed should allow us to classify molecules with organic photovoltaics or not, which will supposedly give us a good model for the efficiency into the Gaussian process. So that's the good news. And let's see, we have more data about that. So the number of descriptors we get, 29. Out of the 200 molecules, actually not 200 molecules because, okay, we have like 3 molecules that are wrong and an error that remains constant at around this range of the regularization parameter of around 0.008. And at this point, it looks like we're in business. So we do more sophisticated versions of estimating the error, which you have to do in machine learning. So that's called cross-validation. And that basically means that we divide the 200 molecules into 5 groups. And we do the learning in 4 of those groups. But to make sure that we're not overfitting and the error that we're reporting is not too low because we're just learning that particular, the molecules on those 4 groups, then we actually look at the 5th group that we didn't use for the learning and we calculate the error there. So that's called cross-validation. And we do that when we have 5 groups. So we use, as the validation said, the one we use to measure the error, we use one of those 5. So that's the 5-fold cross-validation. And the errors are a bit higher, but still looking pretty reasonable. This one in particular turns out to be kind of high, but for the most part, they are, pretty reasonable error. The validation set is actually smaller, so the jumps you tend to get are kind of higher because it doesn't have that many molecules, because we don't have that many molecules to stay with. And we get, less descriptors now than we used before. We can fix that by moving the regularization parameter and playing tricks like that. But the problem we really have is that, okay, so we're using the genetic algorithm to do all this learning. And turns out that the descriptors that we get are kind of very sensitive to the particular set in the cross-validation. So that's part of the problem. And also because we're using a genetic algorithm, there's nothing telling us that we're actually finding a good minimization of the optimization problem, and the optimization problem is the problem that gives you the set of descriptors. And indeed, if we actually run some sample test data, so in particular, this is artificial data where we have between 0 and 60 random descriptors, and we hide one descriptor among them, which is perfectly correlated. So one of the descriptors just tells you 1 or 0, this is a good molecule or not. So when we do the learning, we're supposed to pick up that one descriptor, which is the only one that has information about the property we're trying to measure. All the other ones are random. And the problem is that the number of descriptors grows up, we start picking up a lot of noise. So different colors are different population sizes for the genetic algorithm. And we would like to have this line here all the time. But it turns out that we can pick up noise. This is just one test. There are other tests we do. And the basic point is that the genetic algorithm is failing. So that's part of what you see here. So we have this optimization problem that we need to solve the machine learning, that we need to predict what are good molecules, and the genetic algorithm is failing. Okay, well, one thing we need to do is to do better classical algorithms, in particular Tabu search. So that's really something we're working on right now. But we can try to do something different. The something different starts with turning our initial problem of optimizing our these strong classifiers into what is called a quadratic unconstrained binary optimization. And the idea here is you want to turn the optimization problem into a problem where it minimizes our binary vector omega, quadratic function with this matrix Q. In the diagonal of Q, what you put is a measure of how good every one of these weak classifiers is, and the regularization parameter. So the diagonal here just says that you want to have ones in omega for every descriptor that is good, and the better the descriptor, the higher the tendency to get one in the optimal solution of that problem. So, and one means you choose that descriptor for the strong classifier, and therefore for the Gaussian process. So this is actually pretty easy to solve if you just do that. But you don't want to have a lot of redundancy of the set of descriptors you do. So you do like DFT, let's say, and you do DFT with different functionals, and they're sort of similar. They give you sort of similar results. You don't want to have 10 descriptors that are just the same property with 10 different functionals because they all look alike. So you want to avoid getting descriptors that are correlated, and that's what you put in the off diagonal. And the offset is that the point is that you tend to have ones for good descriptors, but if you pick two descriptors, you pay a penalty which is proportional, and that's another regularization parameter, to the similarity between these two descriptors. So now we turn the optimization problem into a quadratic unconstrained binary optimization problem. So that's good because that works well with Taboo. But another good thing is that finally we have a problem that we can run in the D-Wave chip. So the idea is that this QUBO problem is really a version of a 2D random Ising chain. So this is the Hamiltonian for the Ising chain. In the elements that were in the diagonal of the QUBO problem are just local fields. This is poly sigma C. So they're just like local fields on every one of the bits or qubits of your Ising chain. And the couplings within different spins in your Ising chain are the off-diagonal elements of this QUBO problem. So we have a quadratic problem that solves our inner machine learning problem, and it is an Ising problem. And what you can do is what has been mentioned several times today already. So actually, I think the first paper doing this is due to Farhi that explained it this morning, where you can just initially have a strong transverse magnetic field that will set your quantum state now into a superposition of all possible states in the computational basis. And if you slowly turn off the transverse field and slowly turn on this Hamiltonian, and slowly means, according to the Adiabatic theorem, 1 over the gap, basically, then you find the ground state of this problem that gives you the set of features for your machine learning, for your binary classification. So that's something we can run on the D-Wave chip, and that's what we want to do, okay? So that's a good feature for us because we have this machine there. There are other good features. You can actually try to do fairly complicated problems. So the problem I was describing today, if you notice from the initial description, it's actually like a real world problem where we're going to be trying to optimize over 10 millions of molecules. We're running tests over the 200 molecules right now because we're still doing the learning. But, descriptors coming from a standard commercial software. But at the end of the day, the Ising model really gets these numbers, which are just the correlations between the weak classifiers and the quality of the weak classifiers. So all the processing to get these numbers, you do it in your laptop. And the problem of optimizing for the machine learning, which is the complicated bit, that's what you can do with the machine learning. And the number of bits you need goes with the number of descriptors in principle, but there are techniques already reported by Hermun and Vasil and the D-Wave guys to sort of break it into pieces and still run it into the D-Wave chip even if you have more descriptors than qubits. So it doesn't scale with the number of molecules or the size of your training set, it just scales with the number of classifiers, and you can break it into pieces. So when you break it into pieces, and for some other reasons related to how the hardware works and even physical noise, you're not necessarily going to get an exact solution. But because we're doing machine learning, approximate solutions are okay. Right? So if you get a set of descriptors, which is not necessarily optimal for your training set, you still can have a good classifier, a good fit into your problem, and nothing says that the optimal solution for your training set is actually what you want in general. So we can tolerate error. We would really like to get some potential speed up compared to other servers, so I'm not addressing that. But that's not the only thing we would like. Also, maybe training your classifier this way to try to give you better solutions. And that's something you cannot really establish analytically, and it might depend from problem to problem. So it makes sense to, let's try to run this process. Let's see what model we get out of it, and let's see how well it compares to the best we can do without using the D-Wave chip, which is what they did at Google. And some of the results they got were already quite encouraging. And in some metrics, they were actually doing better with the D-Wave chip already. So that's kind of part of the motivation of this whole line of work. There's no reason why that shouldn't happen here, although it might not happen here. And well, at the end of the day, we get this function that we can run on the 10 million molecules, and on any other molecule, we can report it in the literature, because the function that you get is this Gaussian process that runs on a classical computer. Okay, so that's the clean energy project, which has been running for a long time, and I just want to encourage everybody again to just download the screensaver to do the DFT calculations for this project. And in the last couple of minutes of my time, I guess I can just try briefly to say some of the things we are starting to do with the D-Wave chip, not from the application point of view, but addressing the physics of the chip and what it's actually capable to do in models which are way simpler than these, things like 1D randomizing chains and things like that, where we can understand the physics a lot better. Because as an application, this is, I think, a very interesting thing to do, but it's very hard to extract information about the metrics of the chip itself, because it's under all these other layers related to machine learning. So we also want to address physics questions that, well, a lot of it, D-Wave has been published in later papers for quite a while, so we're catching up with that too, but we want to get independent results also. And I'm just going to talk about one of the things we're doing, which is looking for entanglement, but we've been thinking about this for quite a long time. Turns out it's very hard to actually measure entanglement in the chip. So that there is experimental reasons for that. It's just the way the chip has been designed. So we cannot experimentally look at entanglement, but the chip is quite well understood because it's been, designed carefully and it's been tested in many different ways. So we're using that to sort of talk about entanglement. Entanglement is just one of the things that come up all the time, but I know a lot of, people already know that maybe entanglement is not really the one thing that you need for mixed-state quantum computation, for instance. Maybe it's Discord, So that there are other things you can say about it, but it's one reasonable thing to look at. So, by looking at the physics of these things that Mohammed described yesterday, the energies that you get on this flux qubit are of the order of gigahertz, so you get dynamics of the order of nanoseconds. You get dephasing in the instantaneous eigenbases in around like 10 nanoseconds, which is quite a lot of dephasing. Actually, the dynamical time scale is like 40 times faster than you dephasing, but dephasing is still quite powerful. Now, and I think that was part of the message in Mohammed's talk, this dephasing is on the instantaneous eigenbases. And dephasing on the instantaneous eigenbasis for adiabatic quantum computation is not a bad thing, because you want to be in the ground state anyway. You don't want to be in a superposition of states in the instantaneous energy eigenbasis. The problem is things that move you to excited states. And that's a sort of, in principle, a different time scale. But that's related to thermalization, which is actually quite fast. So that's the other problem that worries us. So this is quite a complicated problem to address. But what we do have is we have a lot of papers that DWIF has been publishing, but we also have simulation code that they have used for their papers, where they check that the simulation code maps very well to the measurements they're actually doing. So we're at least confident about this simulation code. And even if you forget about the DWIF chip, I think it's still an interesting problem. Under these conditions, do you have entanglement? One of the things you will look for. So we look at some instances running the simulation code that was actually developed by Mohammed and Richard Harris. And turns out for the problem we were looking at, we didn't find any concurrence for different pairs of qubits. So I think Mohammed has seen concurrence in the past. So we should try with different Hamiltonians. But what we can do, because when you look at concurrence, you're basically looking at entanglement between only 2 qubits. And we were running a simulation with 8 qubits, so you're tracing out over a lot of stuff. So then maybe it's because when you're tracing out over a lot of stuff on a density matrix, which is already fairly noisy, the entanglement might be swapped away under you trace out, and maybe entanglement was there originally, but it's just that you're not looking at the right place. So we're lucky that Federico actually did his PhD in part on looking at this exact kind of problem. So he already had code on doing detecting entanglement, doing something that is called PPT symmetric extensions. So I'm really out of time, but you can read their papers. They're already published. So the point is that this is an approach that you can turn into a semi-definite program, that you can run fairly efficiently, and it will tell you if there is entanglement or not, and it actually gives you a witness. So Federico did that, and this is what we had. In a range of temperatures from 0 millikelvin to 100 millikelvin, and in an adiabatic time for this particular Hamiltonian of 1 microsecond, using the Redfield code, which is coupled to the environment and quite noisy. You sort of see entanglement there, which, if you look at the energies, that's where the gap is. And this is entanglement between 1 qubit and 3 qubits, even though in this case there was not concurrency when you were looking only at 2 qubits. We have also looked at 2 qubits against 2 qubits. We also see entanglement there. We don't really, don't pay attention to this number because this is just using the entanglement witness. It's not really a measure of entanglement. But we see entanglement where it's supposed to be with a Redfield code that includes the thermalization and the dephasing in the right dynamical scales. So, just to give you an example of things we're looking at. So yeah, I will conclude there. Thank you.
I wanted to ask you one question about entanglement and dissipation. So kind of feel instead of looking into this murky entanglement business with fast decaying qubits, can you use something that is conventional in condensed matter physics? For example, you have a Ising chain, quantum Ising chain in transverse field. You can measure the correlation lengths close to the point of criticality and see how that correlation length depends on the size of qubits, right? It has to be of the order of it. If it's really a global, you would say entanglement. I would say it's a critical behavior where spins are correlated on a length equal to the chain size.
So correlation length for a 1D chain, okay. So
it's something simpler than, I don't know, but it's conventional and would give you.
So we're looking at similar things, actually not just numerically, but running actually on the chip and just getting statistical results from the chip. Not exactly looking at the correlation length. And this is the sort data we've been sharing with other people that were addressing like similar questions. And so far we see a finite length. So we were actually looking for domain wells for instance, or fidelity if you want on a 1D chain. And we don't see it going all the way to 0 as we increase the annealing time. It kind of flattens out after 140 microseconds, looking at chains which are fairly big. So the biggest ones we ran were 84, I think. Yeah, 84. The size of the domains? I think the average size was around maybe 10. The problem with that, though, for these 1D chains, is that it's a problem that is very sensitive to disorder. So there are, tons of papers and approaches about that. This one particular problem, and basically the couplings and local fields in the chip are actually, physical currents on the flux qubits, and they are not exactly 0. So as soon as you introduce some disorder, in this particular model, it's related to a lot of other models that have been studied. Ben Reicher has a paper about, how to get exponential gaps in this chain. Things like, I think they're called Fisher phases, right? Things like that. So it's a model that is very sensitive to disorder. And there is, even if there wasn't any noise, which there is, there is disorder in the chip, in the local fields and couplings. Yeah, we're working on that. I cannot answer. We're gathering experimental data, but we've been doing this for like 2 weeks, so that's one reason why I'm not presenting anything. So, it's also complicated for us to look exactly at the phase transition. That's another thing. But, we're talking with people at D-Wave to, do this kind of stuff exactly. So Mohammed and other people. So we're looking at that. That's very good idea.
Other questions? Okay, let's thank Sergio again.